So far, and I'm going to restrict this discussion to parabolic equations still. We're going to move on to hyperbolic equations later on. So for parabolic PDEs, we have done, as I said, forward Euler, which is first order accurate in time. The Runge-Kutta method, which is what we're going to discuss today, is a method that enables us to solve initial value ordinary differential equations. Okay, it was originally developed for that purpose, and we can systematically derive higher orders approximations of this method. So here we are going to talk first about the Runge-Kutta method for single ODE. Okay, again we are switching gears sort of backwards from PDE to ODE. Okay, we're going to talk about a single ODE, and then we will talk about how to improve the order of the method. Okay, which is really the whole idea here. And then after that we are going to talk about its advantages, disadvantages, and how those can be circumvented. And then finally we will apply the Runge-Kutta method to a system of ODEs, okay, which I am calling the vector case. And I don't have it here down below, but ultimately at the end of everything we're going to apply the Runge-Kutta method, that is the vector rendition of it, to solving PDEs, which is really our interest. Okay, so that's the flow of what's going to happen in today's lecture. So let's talk about first the formulation of this method for a single ODE. Now, how many of you have used the Runge-Kutta method for something that you've done? Okay, so many of you have. I mean, it's a very popular method for solving ODEs, as you know. So the basic idea is this. So we are starting with what's called an initial value problem. Okay, notice that this equation here has no derivative in space. Okay, it's basically just a time-dependent equation. It's kind of like a lumped parameter model of some system. Okay, and it has only one initial condition, so that's why it's called an initial value problem. Now we can apply the forward Euler method that we are familiar with, discretize the time derivative as phi t plus delta t minus phi t divided by delta t, and then on the right hand side, as you can see, the function is being evaluated at time t, and in case the function is also a function of phi is also evaluated at time t, which makes it an explicit method. If I were evaluating the right hand side at time t plus delta t, then it would become an implicit method. Okay, the order of the method is first order, as we know. So the objective is now to derive a time marching scheme that is of higher order accuracy. Okay, so to do that we propose to use two different functions, capital F1 and capital F2, defined as follows. So F1 we'll define as delta t times the function f, which is, this function is often called the driving function or source function. Okay, so delta t times that, and then another function which is that same function f, but now evaluated at a different time instance and a different value of phi. Okay, again, some problems may have this function as only a function of time, some problems may have that function as only a function of phi, and some problems may have it as a mixture. Okay, later on when we apply it to PDEs, you will see that for the specific case that we are interested in, it will only be a function of phi, not of time at all. Okay, but we can generalize the whole procedure. So with those two definitions, and we are now proposing, this is what basically Runge-Kutta proposed, those two authors proposed. They said, okay, how about we write phi at t plus delta t as some value of phi at a previous time t, and then a summation of those two functions with certain weights w1 and w2. Okay, so here in this function we have two unknown constants, alpha and beta. As I said, they are to be determined, and we'll see how we determine them. And then here we have two weighting functions, w1 and w2, or two weights that are also to be determined. Okay, So that's the proposition, that we have those two functions, capital F1 and capital F2, and we make use of them to come up with a formula for integration. Okay. So as I said, these unknown constants are, or they are constants that are unknown at this point, and they may be determined by matching the proposed expression, which I showed on the last equation, with an exact Taylor series expansion. So how do we do that? So this is our proposed expression. We want to match that to this expression. Now think of it this way. If I can match up to, let's say, this term, then my scheme will become second order in time. If I can match up to this term, then my scheme will become, well, actually it shows up as second order, but it's actually first order, because in the end I'm going to divide the whole thing by delta t. Okay, so if I can match up to this term, I get a first order expression or scheme in time. If I can match up to this point, then it becomes second order in time, and so on. If I can match up to this point, then it becomes third order in time, and so on. Okay, so that's the basic idea. How can we match this expression to this Taylor series expression or Taylor series expansion, and depending on up to how many terms we match the expressions, we get different schemes, different order schemes in time. Okay. So what we are going to do to make that comparison, and let me just get rid of this so we can clearly see this, is we are going to substitute the expressions that we had in the previous page for F1 and F2 into our basic proposed formula. Okay. So F1 was this guy here, delta t times F. Okay. And F2 was, if you go back, it was delta t times F at t plus alpha delta t plus phi plus beta times F1. This is actually F1 right here. Okay. And this whole thing is actually F2, this part here, if you go back to the previous slide. Okay. So that's what we've done. We've just substituted it. And now what we are going to do is we are going to take this second term here and perform a Taylor series expansion of that. So F at t plus alpha delta t, phi plus beta times this term here becomes F at t alpha plus alpha delta t times df dt plus beta delta t f t alpha df d phi. Those are the first order terms. Now it's sort of a multi-dimensional Taylor series expansion because f is a function of two variables, t and phi. Okay, so this is like a two-dimensional Taylor series expansion. Those are the first order terms, and then we have second order terms, okay, which has d square phi dt square, or sorry, d square f dt square, d square f d phi square, okay, and then mixed derivatives also show up. Okay, everybody understand that? So this is just a two-dimensional Taylor series expansion. Think of f of x and y. You're doing f of x plus delta x, y plus delta y about f of x and y. Okay, that's basically what we're doing. And then, of course, you're going to have higher order terms, which will be the third derivatives and so on. Okay. So if we now gather all the terms on the right hand side or similar terms on the right hand side, this is what we end up getting. Okay, we get a term which has a delta t in front of it. We get another two terms which have delta t square in front of it, and then we get terms which have delta t cubed in front of it. Okay, which is to be expected because this is a Taylor series expansion in time. Right. Our governing equation is this. All right, if we differentiate this with respect to time one more time, okay, so second derivative with respect to time would be ddt of f, the function f, and that, because it's a function of two variables, we can write as df dt plus df d phi times d phi dt. Okay, So that, and then this guy here is the same as that from the governing equation, so we plug that in here. All right. So that's our d square phi dt square. We are now going to take our original Taylor series expansion, which we had, and here we would get d square phi dt square in the original Taylor series expansion. Okay. We replace that by this expression that we just derived. Okay. And so that gives us, so notice that what I've done here is your original Taylor series expansion was phi at t plus delta t is equal to phi at t plus delta t times d phi dt plus delta t square over 2 d square phi dt square, right? That's my original Taylor series expansion. Instead of d phi dt, I have plugged in this guy, so that's how I end up getting that. And instead of d square phi dt square, I've plugged in what I've derived here. That's that term. And the third order term, I've just kept it as is, not changed that. Okay, everybody got that? All right. So now what we are going to do is, this is the expression we had derived earlier. So going back, okay, right here, from the proposed expression, that's our equation 1. And this is the expression that we have from the Taylor series expansion. Okay, after some modifications that we just did. Okay, now we are going to compare these two equations and see if we can match them term for term up to a certain order. Okay, so if we want to match them, for example, if we want to match this term here, okay, clearly you can see W1 plus W2 must be equal to 1. Okay, so similarly, if you want to match this term with that plus that, well, just that, okay, then you have alpha W2 is equal to half from here. Okay, similarly, beta W2 will be half again right here. So we're just comparing terms and we end up getting those equations. Anything beyond that, the cubic onwards, we are throwing away. Okay, so we're matching only up to the second derivative, or the delta t squared term. All right. When we do that, these are the equations we get, the relationships. Notice that we have 3 equations with 4 unknowns. The 4 unknowns are alpha, beta, W1, W2. Okay, and we have 3 equations. So therefore, we have some flexibility in choosing one of the unknowns to get the others. Okay, and the common way to do it is to choose W1 and W2 equal and equal to half, obviously, because that's going to satisfy that relationship, and then alpha and beta equal to 1. Okay, that's one of the choices that's traditionally used. You don't have to use that choice. Okay, it just makes the scheme kind of elegant and symmetric. All right. So once we have that, then we plug it back into our original formula. Remember, our original formula was phi at t plus delta t is equal to phi t plus W1 times F1 plus W2 times F2. Okay, that's what we have done here. W1 and W2 are equal to half. Okay, and therefore we end up getting this formula. Okay, the truncation error, the terms that we have thrown away are these terms, the cubic term. Okay, so that's our cubic term right there. Okay, now this does not mean that it gives us a time discretization scheme which is third order accurate. Because what ends up happening is, and I'll show you this in a moment, okay, is that you end up dividing by delta t ultimately, okay. But that's the scheme. So what this is telling us is, if I start with an initial condition, let's say at time t equal to 0, and I evaluate these functions f1 and f2, then I can find out what the solution will be at a different time, at a time removed by delta t from the initial time step. Okay, so it's just time integration. That's what that formula represents. Okay, now what we are going to do now is divide this by delta t, this whole equation, move this guy over to the left hand side and then divide through by delta t. Why? Because we want to compare this with the forward Euler scheme, which basically had this term is equal to f of t phi plus epsilon delta t. That's what we had for the forward Euler scheme. Okay, but now we have a slightly different formula on the right hand side, and this is of order delta t squared. So this is why this is known as a Runge-Kutta scheme of order 2, okay, or RK2, second order Runge-Kutta, because the temporal accuracy is delta t squared rather than delta t. Okay, you can follow the same derivation and go up to the delta t to the fourth term and match them, and when you do that, then you can end up getting a scheme like that where f1, f2, f3, and f4 are defined as follows. Okay, so when you do that, then in this case the error is going to be delta t to the fourth. So that's a fourth order Runge-Kutta scheme. Okay, so that's the basic idea, that you can keep matching the Taylor series expansion to the proposed formula in a hierarchical manner, and depending on how many terms you go up to, you can get a higher order scheme of that order. Okay, any questions so far? Here's a little example of using it and then kind of assessing its accuracy. So I'm looking at a simple ODE in time. Okay, so my forcing function f is just a function of phi. There is no t there, as you can see. Okay, so I integrate it, I rearrange it. D phi over phi minus 1 is negative 2 dt, so that gives me a log of phi minus 1 is negative 2t plus c. I plug in my initial condition, which is phi at 0 is equal to 0, and that, when I rearrange it, I get this expression. This is my solution. This is the analytical solution to the problem. Okay, it's an exponential decay in time. So now if I compare forward Euler, RK2, RK4, three different schemes. Okay, we're going to use, let's say, a time step size of 0.1. Okay, the forward Euler maximum time step in this case is 0.5 seconds from the stability criterion. Okay, now the stability criterion for ODEs is slightly different from what we have learned in class, but I'm not going to get into that because that's not really our focus in this class. Okay, now the stability criterion of ODEs, there is no sort of one formula which will give you that stability criterion. It actually depends on what the forcing function is. Okay, so it's a little bit more tricky than the PDE that we looked at. In the PDE, actually, the forcing function is always, which we looked at, is always del square phi del x square. Okay, so we know what that forcing function is. But in this case, if we add an arbitrary f to the right hand side, how stable the scheme is, it will depend on how nonlinear that function is, or what the behavior of that function is. Okay. But in this case, it's 0.5 seconds, and let's say we compute 10 time steps. Okay, so time going from 0 to 1 second. Okay, here's your analytical solution with the formula that I just showed you in the previous page. Here are the solutions of the forward Euler method. Okay, so you can see there is significant error at all time steps. I mean, this is 0.18 versus 0.2, 0.32 versus 0.36. In some time steps it's larger, and then as you get to steady state it becomes, again, the error becomes smaller. This is something we have kind of seen before. Remember those plots I had shown you where the error increases and then starts decreasing again as we go towards steady state. Okay. So that's our forward Euler. Here's RK2. Already you see quite a bit of improvement. We already are capturing the answer up to the second decimal place. Okay. So 0.32, 0.32, 445, 448, okay, 55, 547, and so on. So pretty close. And by the time you get to RK4, the answers are almost accurate up to the fifth or sixth decimal place. Okay. You can see here 18126, which is exactly what we have here. Look at the last one here, 86466, 86466. Okay. So significant improvement in accuracy when you go increasing orders, which is what we expect. That's not big news, but we just wanted to confirm that, okay, with a numerical experiment. Any questions? Now, with the increased accuracy, you also have increased computational effort. Okay, and this is something we have seen again and again, that there's always a price to pay. So, and this is why Runge-Kutta methods are sometimes not preferred by people who do explicit integration in time for a living, okay, because of the computational effort. And it's pretty straightforward to see. In forward Euler method, you require one functional evaluation per time step. Because why? Because you have phi at t plus delta t is equal to phi at t plus delta t times f t phi. Okay? This is your formula for the explicit Euler method. What does that mean? You have to evaluate the function at least once. Okay? You get to RK2, this becomes that. Okay? These are basically nothing but functional evaluations. So now you have two functions to evaluate. You get to RK4, you have 1/6 of f1 plus 2f2 plus 2f3 plus f4. Four functions to evaluate. Okay? So depending on what method you're using, the number of functional evaluations increase significantly, and that's where your cost is. How many times you evaluate the function? I mean, here we have a very simple function, but for a lot of problems the function may be very complicated. Okay, and that's where all your cost will go. So to circumvent this problem, people devised what are called multi-step methods. So the Runge-Kutta methods are known as single-step methods. As you saw, to compute phi at t plus delta t, all you need is information at the previous time step, phi at t. Okay, nothing else, and the functional value at that time step. Okay, multi-step methods make use of solutions not just one time step before, but also many time steps before. Okay, so you can go t minus delta t, you can go t minus 2 delta t, t minus 3 delta t, and so on. Okay. So the downside of multi-step methods, of course, is that they cannot be used in the initial few time steps because solutions previous to the initial condition are not even known. So when you start your process, let's say you want to calculate your solution at the first time step, you don't have 2 or 3 solutions before. You have just one solution before the initial condition, and that's all you have. Okay, so that's one of the problems. Another downside is that you have to store the solution at different time steps. Okay, it's not when we typically do time marching, we don't store the solutions at all possible time intervals. We just reset the initial condition and move on. Okay, and then we print out solutions for time instances that we are interested in. So the memory is really on the hard drive, not in RAM. You understand what I'm saying? So it's a difference between storing all the information versus printing it out on the fly whenever we need it. Okay? If you're solving, as I said, explicit time marching methods are typically used for problems which have very fine grid resolution. Okay? Like DNS of turbulence. You may have 1 billion grid points. So 1 billion times 5 is quite different than 1 billion times 2. Okay? So the memory matters because you are actually storing it in RAM, in your memory, as opposed to saying, okay, when I reach the 100 millisecond mark, I'm simply going to print out the data on my hard drive and then post-process it later on. Okay? That's hard drive memory, which is very, very cheap and easily available. I mean, you can have computers with, terabytes of hard drive space, but you don't have computers with terabytes of RAM. All right? So that's the difference. So that's one problem. Now, the first problem is circumvented very easily. What people do is they usually run maybe 5 or 6 time steps of, RK2 or RK4, typically RK4. And then from that point onwards, they switch gears and use the multi-step method. Okay? So your order of accuracy is not sacrificed because you're still using RK4. Let's say if you want 4th order accuracy. Okay, you're still using RK4. The first 4 time steps may be quite a bit more expensive than the other time steps, but it's only 4 out of maybe thousands of time steps you're computing. Okay, so it's not such a big deal. But that's the typical procedure people follow. So talking about multi-step methods, this is one of the most popular methods. It's called the Adams-Bashforth method. There is another method called the Adams-Moulton method. Okay. The Adams-Moulton method is actually a modification of the Adams-Bashforth method. It's just there's a predictor step and a corrector step. You can look it up in standard numerical methods textbooks. Once you understand this, it's fairly easy to understand how to do that. It's just there is an additional step. Okay. So here is what happens in the Adams-Bashforth method. Our governing equation is that. Again, we are still talking about ODEs. So once you integrate, this is what you end up getting. Okay. So you notice that it's doing functional evaluations here, 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 but those functional values have already been calculated in the previous time steps. It's only a question of just storing them. Okay. So when you start, let's say you are at the, now of course, as I said, you can't use this in the first time step, but let's say you are at the 5th time step. Okay. So 5th time step, when you are going from the 4th time step to the 5th time step, okay, you're basically using the functional values at the 4th time step, at the 3rd time step, at the 2nd time step, and the 1st time step. But those are all things that have been computed already because you already have arrived at the 5th time step by then, and you know the functional values at the previous time steps. You simply use them. Okay. So really, the only thing it requires is one functional evaluation. That's this guy at this point. Okay, all these guys have already been computed before, and you just stored them and used them. Okay. The order of the method, you can see it says delta t to the 5th, but of course we are going to divide the whole thing by delta t to determine the order. So really, it's 4th order accurate. So it's 4th order in time, just like RK4, with significantly reduced computational effort. Okay. And as I said, this is again derived by using Taylor series expansions. Slightly different approach than the RK method, but one can actually derive this by repeated substitutions in the Taylor series expansions. So that's the idea. Now, in the Adams-Moulton method, what happens is this step is actually used as sort of a predictor step, and then there is a correction step. And what that correction step does is it increases the order of accuracy to 5th order. Okay, So that's the only difference between the two methods. I can show you the formula in a moment. It's just another formula like that. All right. Any questions in terms of, so if I asked you to implement this, this would be fairly easy to implement. So if I go back to that table that I had earlier, okay. So what you will do is you will do RK4 up to here, and then from here onwards you will switch gears to the other method. That's all. Okay. All right. Moving ahead. So now we are talking, so far we've talked about single ODE, but now we're going to talk about multiple ODEs. Okay? So suppose we have a system of ODEs which are coupled. Okay? So you can see phi1 depends on phi1, phi2, phi3, phi4, all the phis. Phi2 depends on all the phis, and so on. So they are coupled simultaneous ODEs. This is a vector form of initial value problem. Okay, and then you have these initial conditions. Right? So we can write it in vector form just for the sake of compactness. So we can define a capital phi which consists of phi1, phi2, phi3, phi4, and so on. Okay, and then the function on the right hand side. So this is our capital phi really. Okay, so you can see here that's the definition, and then the capital F or the bold F is nothing but comprised of the individual functions. This is kind of like the notations we are using here is what we had used for the Newton's method when we did Newton's method for a system of nonlinear equations, which you are familiar with already. And then phi naught, capital phi naught, we are writing as the vector comprised of the initial conditions. Okay, so when we do that, we get exactly the same formulas if you go through the derivation as the scalar case. Okay, so this is what you get. Phi at t plus delta t is that, and then these are of course now vectors f1 and f2. Okay, but essentially the same thing. Every scalar now becomes a vector. And then similarly for RK4 we get the same thing. Okay. So we have those. Okay. Now this is just a background. What I'm showing you here is really a background for what we are about to do, which is apply this to PDEs. So that's the vector form. Now let's see how we can apply this framework to solving PDEs. Okay. So going back, so this method that we're talking about is called the method of lines. Okay. So this is our main interest. We sort of digressed from the main topic of solving a parabolic PDE and went into ODEs, but now we are returning back to that. And how do we apply what we just learned to this problem? Okay, so this is our parabolic PDE. This equation is satisfied at every node x is equal to xi. Okay, node in space, that is. Okay, which essentially means that I am satisfying this at x equal to xi. Okay, and of course the right hand side looks like that. Okay. Now what I'm describing here is really the foundation of, or the distinction between an Eulerian reference frame and a Lagrangian reference frame. Okay. Most of you have learned this in fluid mechanics. The basic idea is this, that if I have, so I'll give you an example here. Okay, so suppose I have a room. This is a room, and let's say I'm sitting on top of some device that can move in the room either on the floor or even hover around in air. Okay. Now, suppose the temperature distribution, let's say we are looking at temperature, Okay, and the temperature distribution looks like, for example, this corner is hot and this corner is cold. Okay, and let's say this is hot, this is cold, this corner. That's what the temperature distribution looks like. Okay, so when I go, if I, let's say the system has reached steady state, what I've drawn here is the steady state solution. Okay, hot on the top, cold at the bottom, all right, in that room. So suppose I go from here to here, okay, will I observe a change in temperature? I will, right? But if I had a probe here and I monitored the temperature as a function of time, will I observe a change? Remember, this is the steady state solution we are talking about. Okay, we will observe no change. Okay, so what's going on here is that the change, so if when this person is moving in the room, he observes a change. That change could be due to two reasons. Either because the temperature in the whole room is changing with respect to time, okay, or because he's moved from one point to another and the temperatures of the 2 points are different. Okay, so his change, the change he observes, okay, could be either due to change of the whole solution with respect to time or due to change in, you know, his location going from one spot to another. On the other hand, if that person was just sitting here and observing things with respect to time, in this particular example, he will see that nothing has changed. Everything is constant with respect to time. Okay, so that's the difference between a Lagrangian description and an Eulerian description. In a Lagrangian description, you simply are sitting on top of your probe, so to speak, okay, and the probe is moving around and you're observing a change, and that change could be either due to the change of your location, the location of the probe, or due to the fact that the actual dependent variable changed values, okay, with time. All right. Whereas in an Eulerian framework, which is what we are doing here, okay, so this is an equation derived in an Eulerian framework. Here what we are saying is we are fixing our attention, the probe is static, or we are fixing our attention to one point in space. Okay? So in a broad sense, in a Lagrangian framework, all functions are a function of time only. In an Eulerian framework, all functions are a function of time and space, or variables change due to time and space. In other words, when you go from here to here, the temperature may be different. Okay? But in a Lagrangian framework, you are sitting on top of that probe and that probe is simply moving and you're observing how things are changing with time. Okay? So this is really what this whole idea of method of lines is based on. It is saying that, okay, I start with that equation, but that equation now what I'm saying is has to be satisfied at every point. And at that point, I am thinking about, okay, if I'm sitting on top of a node, okay, I'm thinking about what else is influencing my nodal value. Okay, and it's saying, okay, the nodal value, the rate of change of the nodal value with time depends on what are the nodal values surrounding me and my own nodal value. That's all. Okay. So what we can do here is that we can say that, okay, if I now think about this equation here, this guy, okay, I can say the change of phi with respect to time is occurring because phi itself, so the forcing function, so if you think about this, I have d phi dt, this is the ODE we were looking at earlier, is f of t and phi. So the d phi dt can be caused either by a change in phi or due to, you know, some function, some time dependence of the function itself. Okay, so if I look at this equation, I can say that the nodal value of phi at any location I is caused by that value itself, which is kind of like relating that to that, okay, and other quantities which are also functions of time, because those values will also be changing with time, okay. So that's the whole idea, that we are saying phi I plus 1 is some function of time, phi I minus 1 is also some function of time, okay. So therefore the whole framework we can write as, or we can think of it as something like that, okay, that the value of phi at a node changes with respect to time and its own value, or it's driven by a function which changes with time and its own value. All right. Now the problem is that if we say that this guy is a function of time and this guy is a function of time, we don't have explicit expressions for those. We can't say that phi I plus 1, for example, is equal to exponential of t. We don't know those solutions anyway. Okay. So when people arrived at this point in developing the method of lines, they said, well, that's all nice and good, but we don't know how phi I plus 1 and phi I minus 1 changes with time. So how are we going to define this function? Okay. We don't have an explicit form for that function. Okay. We do have an explicit form for the dependence on phi I, which you can see it's just a constant times phi I, but we don't have explicit expressions for the time dependence of those two quantities. Okay. So then they said, well, instead what we can do is we can rewrite this in a different form and say that phi, we can make this a coupled set of ordinary differential equations and say that phi or phi I is a function of itself and two other unknowns. Okay. And we can have additional differential equations for those two other unknowns. Okay. So what you end up getting is something like this. If you think about now your nodal equations, phi 2, for example, its rate of change will depend on phi 1, phi 2, phi 3. Okay. The rate of change of phi 3 will depend on phi 2, phi 3, phi 4, and so on. That's what you have essentially in this equation right here. All right. So what do we have here? We basically have a coupled set of ordinary differential equations. Okay. So what we have done is we have taken the PDE, which is a single equation, and converted it to a set of ODEs. Okay. So that's basically the idea of the method of lines. So it falls within the framework of what we developed for a coupled set of ODEs, and we can use that Runge-Kutta or other ODE solver framework for the vector case to solve PDEs. Okay. So here is our final equation, you can see. So d phi 2 dt. So this is after, I'm assuming that phi 1 and phi n are already known. They're Dirichlet boundary conditions. So we have that. So this is our forcing function. So the forcing function is right here on the right hand side. It is a function of the dependent variable itself and two other unknowns, but those two other unknowns are coupled. They're part of the vector set, the whole vector. Okay. So this is our forcing function, and we can now solve that. The method is called method of lines because essentially we are solving ODEs along lines x equal to xi. Okay. In this case, this is a one-dimensional problem, so basically the line reduces to just one point. Okay. But in general, you would actually do it along these lines. All right. So that's why it's called the method of lines, and this is the basic idea, that you convert a set of ODEs to PDEs and then go on to solve it. I'll show you an example of what happens when you actually implement this. Let me just make this bigger. All right, so this is the example that we were just looking at. So this is our d phi I dt right here. Okay, right there. For I going from 2 to n minus 1, those are our nodal equations. Okay, here is my forcing function fi. All right. And then I have, this is my capital F1. Remember, my capital F1 was just Fi. Actually, in my notes, I had defined it as Fi times delta t. Okay, but so it's actually this times delta t, and then F2 is defined as that. Okay, and so what you do here is, so this is a little bit, requires a little bit of thinking. So this is phi1 plus delta t times F11. Okay, notice the subscript here. This first one is for the function F1 and F2, and the second one is really the nodal index. Okay, so this is F1 of 1. Okay, and then I have phi2 plus delta t times F1 of node 2, and so on, phi n plus delta t times F1 at node n. And so what I have done here is I have taken, so this is my forcing function. Now in that forcing function, if instead of phi I plug in phi I plus delta t f, okay, then I get this new function. That becomes my capital F2. Okay, so it's simply a question of taking this guy and plugging it in for phi 1. So if I put I equal to 1, let's say, okay, then I'm going to plug it in for that guy, and so on. So that gives me this expression. So F2 has been expressed in terms of the F1, and F1 is basically the function itself. All right. Now there are some things you have to kind of worry about when you implement this, when you go to boundary conditions and so forth, but let's not get into the details here. So that's what I'm talking about here, how to do the F1 and F1 or Fn. And then once you do all that, then you can use your ODE solver. Okay, and let me just make this a tiny bit smaller so you can see it. So here is what happens with the, so what I've used here is method of lines with RK2 integration. Okay. The time step I've used here is 0.8 delta t max. Delta t max being the maximum allowable time step for the explicit method. Okay. So you can see here, this is the solution at different instances of time, and here is the actual informative plot. So this is looking at error at the 5th node as a function of time. Okay, so the black curve here is the forward Euler method, and we have seen this curve before. It increases the error and then starts decreasing with time as the system goes towards steady state. Okay. And then this is what you get with RK2 method of lines. You see, if so, of course, the sign is negative in this case, which can happen, as you know, between different methods. Okay, but if you look at the magnitude here, this is about 2.5 10 to the minus 4, and this here is about close to 4 times 10 to the minus 4. Okay, so the magnitude of the error is significantly lower in this case. Now, of course, this error includes truncation errors due to space, as I mentioned earlier. This is not just the truncation error due to time. Okay, but with a higher order time integration, you do see that the error is significantly lower compared to the forward Euler first order explicit method. Okay. Now, in terms of stability, as I said, Runge-Kutta methods, the stability is difficult to define without the forcing function. In this case, the stability is exactly this. The stability criterion is the same as for this particular equation is the same as for the forward Euler method. Okay. So the same time restriction you still have to use, but remember, your temporal accuracy is now increasing with the same time step. Okay. So that's the advantage. There are lots and lots of areas where people use method of lines with higher order time integration methods for explicit integration of ODEs. Okay. Very